Okay, welcome everybody to this last section of the 2020 IPROMO course. I'm happy to introduce you Larry Lopez from the Faculty of Agriculture of the Yamagata University in Japan. He will give us a lecture on climate change and mountain vegetation, biodiversity and society. Please, Larry, the class is yours.
Okay. Thank you very much for the introduction and for the invitation to participate here in this summer school, if I am not wrong. My major is actually meteorology, but I work a lot in forestry, or I have been working in forestry for the last 20 years. I am very interested in the topic of climate change. And I will show you in this presentation the places where I have been very fortunate to participate during doing research, and what is my take concerning climate change. First, a brief introduction. I have been doing research in several countries around the world, always with the main topic of climate change. Japan, where I reside, for us it's very easy to go to China, Indonesia, Mongolia, Russia, and I have been very lucky to participate in several projects, especially the one in Russia and Mongolia was an eye-opener to understand well what is the meaning of climate change in the present, but also how were climate change in the past. And of course, we have also, as with Italy, a very good collaboration with Germany. And in Germany also, we have several joint projects with Hanover University. I will make a very brief introduction of where I am located. This is the map of Japan. I don't know if you can see my mouse. This is Korea, South North Korea. This is China, and here all this is Russia. So I am located in the region of Tohoku, which in English means northeastern Japan. Sendai is one of the biggest cities in Tohoku, and the tsunami area, if you recognize it, took place in all this coastal area, even reached the area of Chiba, where the Narita airport, which is one of the biggest airports in Japan, is located. Tohoku has 6 prefectures. Here is Fukushima, which is famous because of the nuclear accident. Miyagi is here, Iwate, Aomori, Akita, and here is Yamagata. So we are about 500 kilometers away from Tokyo, and we live. The faculty is located in the area of Shonai, which is the part of Yamagata Prefecture that faces the Japan Sea. So from here we are very close to North Korea, and so every time there is a problem with this chubby guy, we always have to be in alert. Okay, so this area of Shonai is where the Faculty of Agriculture is, and here in the south, about 35 kilometers away from the city, is the university forest. So the university has a forest of about 753 hectares where we conduct our experiments. So it's very easy for us to do anything in this forest, any kind of research, without asking permissions to all the government offices that own forest, because this belongs to the university. It facilitates the work and research for us, and education also. So we have a very nice building there where students stay. We usually do summer schools and winter schools with the students from Germany, Peru, Vietnam, Mongolia, China, Thailand, So they come regularly to visit us. And I hope in the future we can do also one with Torino University. This is the forest where we do research. It's a mountainous area. Completely is the part of the Asahi Mountains. The range is from 250 meters to 850 meters. It's not so tall in this area, but if you go more into the middle of the prefecture, somewhere here, the altitude could reach easily 2,000 meters. So in this area, we have different kinds of forests. We have the main plantation area is Cryptomeria japonica, which is Japanese cedar. We have a beach area, which is a Fagus crenata, which is different to the Fagus sylvatica that you have in Europe. We have patches of larch, which is Larix campeferi, which is a different species to the ones you have in Europe. And also we have Quercus mongolica, which is a different kind of oak, which is native of Asia, and a different species of acer, which are the main species. We have other species that are present, of course, in this forest, but they are minor. So we don't count them so much as forests, but they are more in a mixed condition. Well, in this forest, we have, of course, different fields, which is meteorology, hydrology, forestry, and soil science. And all of these sciences are combined to understand the forest ecosystem. So this is more or less a view that we have for the forest. It's a region with high precipitation. I don't know if the next one you can see here. We are located here, and this is that is in Japanese. It means the areas with high snow precipitation. So we are located more or less in these areas, in these mountainous areas, and normally the snow depth reaches about 3 meters in winter, but 3 years ago, we have a snow depth of 5 meters. But there are many extremes. So there is also this last winter we have only 1 meter. So there is a very high variability, which we could assume that is because of climate change, that it's altering the precipitation regime. But in reality, we have data from about 50 years ago, and phenomena like these have happened before. So there have been snow precipitations of 4 or 5 meters in the past, and there have been also a snow precipitation of 1 meter in the past. So it's not very easy to attribute if this is actually a climate change or is a normal cycle. Based on the data, past data, this seems to be a normal pattern. As you can see here, most of the high precipitation area in winter, the snow cover, is located in the areas of Japan that face the Japan Sea because of the strong influence of Siberian wind in winter. This is the precipitation that I wanted to show you for this area. So we have about 3,000 millimeters of precipitation in a year, which is about 5 times of the precipitation in Central Europe. And only in December, we have almost 600 millimeters of precipitation in 1 month, which is equivalent to the precipitation that you have in Europe in a year. And what we call the dry years are the July, April, May, and June, which are in the range of 100 to 120 millimeters per month. The rest of the month, we have from 200 to 300 millimeters. This period of especially April and May are very important because most of the forest and vegetation in this area survive with the snow melt from winter that in spring. So there's a huge amount of water that is released from the forest, from the mountains to the lowlands, especially to the rice paddy fields. So the snow melt water that goes from the mountains to the paddy fields inundate the land, the lowland, and for that reason, it's possible to grow rice, abundant rice in this area in Japan, which is one of the best rice in Japan. And also, of course, the best sake comes from this region because of the pure water. It's a very nice water, nice soil, wonderful weather, and makes a very good high quality rice. So the temperature, as you see here, the average temperature is, of course, not so high if you average the month, but we can have maximum temperatures, daily maximum temperatures of 35 degrees in midsummer, and about -5 degrees in winter. So it's not a very cold winter, and we would say it's more or less a hot summer with very high humidity. So this is the mean temperature, and the annual precipitation is 3,000 millimeters. So now I will tell you more or less my idea or what I have experienced about climate in the study of climate. So I titled this Climate in History. This is a very well-known graph. It has been designed with several papers, and this is what is the change of temperature in the Holocene, because we are now in the, well, it's called the late Holocene, but if we consider that this is the early Holocene and this is the mid Holocene, but it's just names. Anyway, the Holocene started, let's say, 11,000, 12,000 years ago. And from then on, there have been increases and decreases of temperature. So we have warm periods and cool periods all over the history of this Holocene period. The part that really interests me here is the climatic optimum, which is a period in the past, which is between 4,000 to 8,000 years ago, mainly 4,000 to 6,000 before present. And this is a period that is quite interesting for me because I conducted for several years research in Siberia, in the area of Yakutsk, which is a permafrost area. And for me, this is one of the most interesting places in the world because I consider this as a living laboratory natural laboratory of past climate change. So the city of Yakutsk is situated along the Lena River, and it's about 62, 63 degrees north. So it's where the taiga is a beautiful forest of only basically large Larix cajenderi trees and Larix gimelini. And as you can see in the legend, Russia is the Russian Federation, or Russia is one of the very few permafrost areas where everywhere you go, the permafrost is continuous. So it's not discontinuous like you can see in Alaska, or sporadic or isolated or discontinuous as you can see in Alaska or Canada or in Northern Europe. So this is a wonderful, wonderful place to study permafrost and to study what happened in the past. I will go back to the climatic optimum in the next slide. This is an area. This is how the Siberian forest looks from the airplane. It's a very, very beautiful, beautiful forest. It's not continuous, as you can see here. There are these patches of grasslands everywhere, They're like intermingled within the forest. When we did this study here, we used to call them grassland forest ecosystems because they are somehow linked with each other. So I want you to imagine, I will go back 1 second. I want you to imagine that before the climatic optimum, all these grasslands were forest. So at some point in the past, the permafrost under this forest thawed, and all these patches of forest became grasslands. So if we have a close-up of the forest, we will see this. And based on, I forgot to write in the study here, a friend of mine, colleague of mine in Japan, did a study with pollen in these grasslands ecosystems, and he found that these grasslands were formed exactly in 5,000 to 6,000 before present. So exactly during the climatic optimum. So the global warming that took place at that time produced these grasslands. This is what you see below the forest at present. You have huge, they are called, in Spanish it's called cuña. I don't remember how, what's the name? Let me see if there is in the, wedge, ice wedges. These are ice wedges of about 40 meters long, and they are in the soil. And when the temperature in the soil increases to a certain level, the permafrost starts, of course, increasing the temperature too. So this line where it says this means active layer, and this is permafrost. So here it says that in summer the active layers thaws, and in winter it freezes again. So this layer is very active because it's freezing and thawing every day, and the permafrost is always frozen. So when this layer is warm with the higher air temperature, this line goes down, 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 and reaches these ice wedges. So when these ice wedges are reached, of course, all the ice starts melting, and there is no way back. There will be nothing unless the temperature drops right away for the next year, that will stop this process. And this process, of course, lasts several centuries or decades or centuries. And then all this soil and forest sinks. So this is a process that was explained by two Czech scientists in the 70s. I personally met Professor Čudek in Brno some years ago in Czech Republic, and he explained me all this process was really, they really did an excellent work 50 years ago. So this is how the forest, they depict the forest. You have large trees, you have the active layer, and you have the permafrost with these huge ice wedges in inside the permafrost. Wait a second. So, and this is the big question. Why you have these ups and downs in the soil? My theory one day, their theory also is that fire produce burn the organic layer, and at some point these depressions are formed in the forest. But that alone doesn't explain the process. But I think, and this is my theory, that fire combined with an increase in snow depth, and accumulation of this snow melt, because this is more or less a flat area, produces a deepening or an increase in temperature in the soil. And when the temperature starts increasing, the ice wedges melt, and the soil sinks, and the forest at the top, of course, starts collapsing, and they develop, all this water develops a lake, temporal lake, because in this area the precipitation is very low and the temperature, the evaporation is higher than the precipitation. So the water of this lake, little by little, starts evaporating, and the small lake that you see in the middle of the grassland is the only water body that remains at present. There is one question here that was interesting when we started this project, is why the forest doesn't regenerate in this area again. If the seeds are flying everywhere and there is water, why not regenerate? And this is a paper that I wrote in 2007. The permafrost is very saline. So when the water started coming out from the ice wedges, it brought all the salt that is inside the permafrost and brought it up to the surface. So when the water evaporated, the salt was left on the ground, on the surface soil layers, and only salt-resistant grasses are able to grow in this area. And that's why after several thousand years, the grasslands ecosystem have remained very stable. And that's how this was produced in during a global warming that apparently was much more severe than the global warming we have now. And this is also the IPCC in 1990. In Europe, sorry, the quality of the figure is not very nice. This is more present, so I like this graph because it can not only be proved with physical data, but also can be proved with historical data. So especially in Europe, there is evidence that in this period, the medieval warm period was actually warmer than it is now. Of course, there are many models, and it's very difficult to compare physical measurements at the present with estimated data in the past. But at least it seems to me that the warming that we are experiencing now is not as high as the warming that we have in the past. This is I forgot to translate this into English. This is a very famous painting in Japan. This is it's called Sakuradamon Gai, or Sakuradamon Gai no Hen. So this means a battle that took place in 1860. In March 24th, in front of the palace Sakuradam, or in the entrance of Sakuradam. And this is very interesting, this painting, because in March, this is Tokyo, and in March in Tokyo, at present, you don't see snow at all. So the timing when they did this was already leaving the Ice Age, was already the Little Ice Age. But still Tokyo still had very snowy winters. And this is something really interesting that is not scientific, but helps science to prove how was the environment at that time, at the beginning, at the end, almost the end of the Little Ice Age. So I am sure in Europe, you must have lots of paintings and art related to the medieval warm period or the Little Ice Age. And this can be proven not from the point of view of natural sciences, but more from the point of view of social science. How was the climate in the past? I don't know. This was a teaser, basically. This is something that you know very well. It was published in 1999 by Michael Mann. Michael Mann is an American professor. I don't remember the university. And he used 3 rings to calculate, to estimate how has been the climate in the last 1,000 years, but completely ignored what was the medieval warm period and the Little Ice Age. So in classes, what that I do here in Japan, I always like to tease the students, asking them which one do you think is right, the one at the top or at the bottom. So the one at the bottom, maybe you already know, it was reviewed. It was found that the methodology used was not the correct one. And unfortunately, for some years, the IPCC also used this graph. But if I am not wrong, it has not been, it's not in the IPCC. Sorry. Now, this is a study done by CIRO, which is an institute in Australia, which very high quality science that they do in this institute. And they have shown that in the last years, you know, there is a positive feedback of atmospheric CO2 increase because the water use efficiency of plants increases since there is more CO2 available in the atmosphere. I forgot to add 2 graphs that we have tested here in our forest with 2 tree species, cedar and larch. We're using carbon isotopes and 3 rings. We have also found that tree growth has increased and that there is a very good correlation, let's say, with tree growth and carbon CO2 in the atmosphere. It's very clear. The relationship is really very clear. So, which more or less proves what this gentleman found in this study. So, the CO2 can be blamed for many things, but from the point of view of plants, I think the plants are very happy to have an increase of CO2 in the atmosphere. Okay, this is more or less I wanted to give you this background, so to know how I address science based on this background that I have on climate change. I might be wrong, but this is my stand when it comes to study forests and ecosystems in Japan. So I will show you some study cases that we have. This is it's not always only climate change. It's not always anthropogenic disturbances. But as you know, Japan has a very long history of tsunamis. In Japan, when you come, you will see most of the coastal forests or the coastal areas are very windy. There is a very high sand blown effect. So the sand can cover roads and agricultural areas, and there is a very strong salt spray. So the way that Japanese have dealt with that is growing coastal forests or forest along the coast. And this is something you will see everywhere in Japan, from the southernmost island to the northern part of the bigger island, Honshu in Japan, and parts of Hokkaido. So the tree that they use for this forest is black pine. It's a Japanese species. It's Pinus thunbergi, which is a species that only grow here in Japan. So it's not Pinus nigra, the one you have in Europe. And the tsunami of 2011 basically destroyed all the coastal forest in Miyagi, Fukushima, Iwate, which are the main prefectures that were affected by the tsunami. This picture is quite interesting. It's taken from a helicopter. In this picture, the water is still going inland because the airport that you see on the right side is still intact. So this water still goes 1 or 2 kilometers more inland. And this is a flat, very flat area. And the effect, you will see it in the next slide. The effect of the tsunami is double. So there is a double effect when the water goes in, and it's even stronger when the water goes back, because that's the real strength. That's the let's say the massive destruction occurs when the water goes back. This is another picture of the same place that you saw. This is the airport. So this is the Sendai airport, an airport that we in northeastern Japan we use very much because it's the biggest airport. And you see that before the tsunami, I fly with this airport quite often, and I always like to see from the plane the coastal forest. This is how it was before the tsunami, and this is how it stood after the tsunami. So completely destroyed. And of course, all the houses, the agricultural areas, the greenhouses, everything was totally destroyed. So in this area, the airport is, let me see if I find the airport. The airport must be somewhere here. No, sorry. The airport is somewhere here. It's not in this area. But just to show you how was the tsunami here, this is the way it entered. So this area, as I told you, is flat, and the tsunami went very much inland. So when it came back, it destroyed everything on its path, and especially the coastal forest. And in this area, which is called Watanoha, in Ishinomaki City, there was a patch of forest that survived. It's the only or the very few areas where the forest survive. And the reason for the survival of this forest is that the tsunami, there is a small hill here, and the tsunami didn't go so much inland. So when it went back, didn't have the strength that I was telling you about. So it went, well, I wouldn't say mildly, because it still has a strength, of course, went in, but when it went back, it was very short, the return. And the forest was able to survive. So we did one study here. This is the black pine tree. And here I give you only one example. So this is before the tsunami and after the tsunami. And as you see here, the growth was very normal until 2010. And from 2011, when the tsunami took place, the tree rings became very, very small. And we finished this study in 2015. So we consider the study only until 2014. This is we use a special tree ring index for a short period of time. And as you can see here, the growth was quite normal before the tsunami, and after the tsunami, the growth was very small. Sorry for the yellow letters. I will tell you what it is, okay? In 2011, the growth was a bit better than the other years because it was still reserves. That's what I mean from the previous year. And even though the salt in the soil disappeared very quickly because it's sandy area and the precipitation here is about 1,000 millimeters per year, the effect on the tree remained for 3 more years. So, and this is what I call the lag effect. Well, in agriculture, salinity has been studied extensively, and I couldn't find many papers related to salinity on trees. But there are several papers. The letters in yellow are papers' names, so don't worry so much about it. what is the salt creates a hyperionic and hyperosmotic stress in plants, in the cells. And once the roots sense that there is salinity in the soil, the roots send a signal to the stomata, and the stomata close. So because of that closure, the stomata stops taking CO2, and the carbon, this is a carbon isotopes, stop getting carbon-12, and the ratio between carbon-12 and carbon-13 increases. So I don't know if you're familiar with carbon isotopes, but it basically indicates that the stomata is closing. So, and if the stomata closes, you have decrease in not only in transpiration, but also in photosynthesis, of course. So, but what was really interesting was that of course, there was a sharp increase of the carbon isotope caused by the salinity, 1.3 per mil, which is something impossible to have, that can happen in a normal year. But what was interesting to see was that the carbon-13 started decreasing, which is a good sign. It's a good sign. It's a sign that the tree is recovering. And of course, we follow up this, but this study, we ended up in 2014. So we found in a study that was conducted after the tsunami by Ito and Yoshizaki, that in this species of trees, the root, the salt normally is accumulated in the roots. Here, I will show you later at the end. We not only checked carbon-13, we only look at oxygen isotopes, but to our surprise, there was no indication of a change before or after. So we thought that maybe a combination of salt water and rainwater was going to alter the oxygen isotope of the water, but we didn't observe that, which we based our hypothesis on a study that was done in Florida, where Chai et al. Found that when saline water entered the tree combined with rainwater, the oxygen isotope changed, but that was not the case. And we also checked nitrogen isotopes. Actually, most of my studies on isotopes have been on nitrogen, but to our surprise, we didn't find any change. The hypothesis here was that the tsunami removed the A horizon, where most of the nutrients are, and for that reason, the plant was not probably able to catch as much nitrogen, or a different kind of nitrogen that could change the signal. Another report also after the tsunami mentioned that sand deposits that carried from the ocean were deposited in the forest. But maybe in our forest this didn't happen because, as I told you before, the tsunami was so short in distance that was not did not have the strength to remove the soil from the ground, and did not bring enough sediments to change the soil properties. Furthermore, there is mycorrhiza attached to black pine trees in the coastal forest, and this mycorrhiza is salt resistant. So that could also be one of the reasons why the nitrogen cycle in these trees was not altered. Oh, sorry, there is one slide that I miss here, but it will come out probably in another further in the presentation. We have also done studies using SAF-flow and oxygen isotope in cedar forest in the in our research forest. And this is what I will show you in the next slides. I don't know if you're familiar with this technique. This was created by a French professor. Used two needles that basically measure the difference in temperature between them. And this is, to explain it in an easy way, is extrapolated to movement of water inside the tree, and with that you can calculate transpiration. So we use this method. I use it extensively in Russia and also in Japan. Sorry, before I go here, I was supposed to show you this slide before. In Shonai, we have experiencing very strong variability in snow. Sorry? We have been experiencing a strong variability in snow, but what has been something interesting, and this is one of my students, he's a PhD student, he found that in this short period of time, because only 10 years, he found that the rain-snow ratio in winter has been increasing in the last decade, which is something worrying, because trees, as you will see in the next slide, use water from snow melt in spring. And when there is too much rain in winter, the snow depth decreases by the end of the winter season. Okay, so this is what I wanted to show you before the rain on snow ratio. We measure subflow, basically transpiration in the trees, using this subflow method. And this diamond symbols line here is the snow depth. As you can see, in this year, the snow depth was about 3 meters, and it decreased rapidly from the end of March to the end of April. The end of March, so in 1 month, the snow disappears. But what was really interesting in this place, what we found really interesting, because we installed the subflow sensors to measure transpiration the previous year, in November 2011. In April, the snow was still almost 2.5 meters, and the cedar, which is an evergreen tree, started already transpiring. So I was actually surprised that the tree, the atmosphere was connected with the soil, despite all the huge amount of snow that you have above the soil. So once the atmospheric conditions were okay for the plant, so let's say more than 5 degrees in the air, the stomata opened and started transpiring or absorbing water from the soil. Larch, which is a deciduous forest, started transpiring later, once the leaves were formed. And of course, there is also some internal movement, but we can see here that this movement of larch in transpiration means that the tree already has enough leaves for continuous transpiration. So this was a study of a student of mine in 2013, and this was very interesting. We have follow up more studies, and we thought it was only 1 year, but we always found the same, and we have measured soil moisture in winter to see what is the movement, and it was a paper published by my student in 2020. This is the transpiration that we have for cedar trees. Sorry, I didn't write the year here, but this is 2016-17, if I'm not wrong. No, 17. And as you can see here, the transpiration already starts in mid-March. So when we still have plenty of snow on the soil. So the transpiration is about 200 millimeters during the season, which is not so much compared to the precipitation that we have for this area. This is data that we obtained with a subflow, and this is, well, we did it for every month, and we divided what was the percentage of precipitation for every month. So here is also quite interesting because the precipitation is not very well distributed in summer, but we have almost the same transpiration for all months from April to September. So it means that the soil is always very well supplied of water. So, which is, we assume is normal because of the high precipitation that we always have during the year. And this is something also that we find. Yes.
It's if you don't mind, now it's time for the questions.
Okay. Then I stop there. It's just a slide, but it's not so important.
Okay, so the question and answer session is open. So please, if you want to ask or write something to our lecturer, please. Okay, there is the first question from Joel.
Yes.
Hi, Larry. Thanks for your presentation. I would like to ask you about the 1999 IPCC graph. What do you think the IPCC does not include this information anymore? Could it be due to new evidences or changes or improvements in research methodologies in these 30 years?
Yes, I think you're referring to the graph that Michael Mann, right? Let's go back here. This one, right? I think, oh, sorry. This one. Yes, after this study, the study by Michael Mann in 1999, I think there was a group of scientists that did not agree with the result of this study. And there was a commission, as far as I know, there was even a documentary on TV of a commission of scientists that verified the methodology used for this study. And they concluded that the methodology was not applied correctly. So the results were not reliable because the IPCC had already published in 1990 the results of where they had found the medieval warm period and the Little Ice Age. So it was impossible that they could be erased. And that's why it was not so easy, actually. It was actually after lots of criticism that it was erased by the IPCC.
Okay, thank you so much. There are other two questions, one from Paula. Thank you, Professor, for your presentation. I have myself lived and worked, researched in Tohoku, and I am now working on a PhD with Tohoku University. So it is exciting to hear about your work and research between Yamagata and Miyagi. Okay, it's more a comment.
Okay.
Another question from Kika. I don't fully understand the main point about the transpiration starting in March. You mentioned it means there's water on the ground, so it's because the temperature is higher.
Yes. Maybe because my background was in colder areas, in Siberia, in Mongolia, in northeastern China, when the transpiration from forest does not start until the snow has completely disappeared. So when I started doing studies here in Yamagata, the soil, as you could see, the precipitation in December is very high. It's almost 600 millimeters. So when the snow falls, the ground is actually very wet. So once the atmospheric conditions are favorable in mid-March, which is basically that the air temperature is higher than 5 degrees, the physiological activity of trees can start. And they start regardless of the snow, of 2.5 meters of snow in the soil. So this is a clear proof that the atmosphere is connected to the soil through the tree. And the snow actually doesn't matter. For the tree doesn't care at all about the snow.
Okay, now there is a question from Paula. How do you say the narrative of climate change has shifted in Japan?
How is the question is how is the narrative?
How do you say the narrative of climate change has shifted in Japan?
You mean from the point of view of how scientists in Japan addressed climate change? If that's a question. For example, I can tell you personally,
Yes.
in Japan, in the at the beginning of the century, I think Japan was very much within the normal train, let's say, the global train of assuming that CO2 was the responsible of climate change. But there was I would say, a shift in the 2010s, let's say 2008, 19. There were several studies here in Japan that did not, let's say, disproved that very subtly, very subtly, that CO2 was not responsible for the CO2, for the increase in temperature. And little by little, that has been let's say, in the general topic, is not mentioned anymore. It's, let's say, it has become very weak argument. And nobody says it, of course, directly, but you can perceive it in symposiums, in conferences, in classes or discussions, that nobody takes the CO2 theory very seriously. So that's, if that was the question. I don't know. I'm not so sure if I am answering your question.
I don't know. Maybe Paula can give us a feedback. Thank you very much. Yes, I guess it's that was the answer she's expecting. Okay, there's a comment from Zana. On previous lecture, we mentioned that the increasing of CO2 is good for trees,
Yes.
but it was observed that many trees are dying more quickly. So trees start to live fast and die young.
Oh, but trees can die of many reasons. You know, this is something that is quite interesting. You know, the lowest level of CO2 in the atmosphere that the trees can stand is 150 ppm. So lower than 150 ppm, the trees will die. They let's say they will starve of carbon. The carbon is starving. At present, we are 400 ppms. 400 ppm is the concentration of CO2 in the atmosphere. And botanists have reached an agreement that 800 ppm of CO2 in the atmosphere is the ideal concentration for plants growing in natural conditions. And there have been many studies with vegetables, with tree seedlings, where the increase in CO2 concentration in greenhouses increases the growth of trees very rapidly. This is what we observed here in Japan, and not only Japan, in many places around the world. The reason why trees die, there are multiple reasons. I would have to see a study that says that CO2, that trees are dying because of an excess of CO2. I will show you later one study that I have, why trees are dying because of too much nitrogen, but I never heard about too much CO2, at least not yet.
Okay, thank you so much. Now it's we are perfectly in time for a 5-minute break.
Okay, wonderful.
So see you in 5 minutes, and please,
Okay.
Larry, when you're ready, just give me a voice.
Okay,
See you in
okay,
5.
wonderful.
Ready, please.
All right. Okay, I just to continue to finish with a study about transpiration. We measure also the radial growth of trees with I don't remember the name of the instrument. It's like a belt that you put around the tree, so you can measure the growth of trees every day if you want, right? So here we found something really interesting, that there was transpiration in April. Actually, it started in March, but that transpiration did not translate in tree growth, which I was expecting, at least stem growth. I was expecting to see some growth of trees during this period. May has almost the same transpiration rate as June, but the tree growth, the growth in trees was completely different. And the same for July, August, September. They have almost the same transpiration as May and June, and still the transpiration value was also the same. So there are many the carbon, let's say, that is being exchanged with transpiration. This is a conclusion that we got, that the carbon that the trees are taking when they are releasing the water through transpiration is used not only, of course, for stem growth, but is also used for root growth, for storage, for leaf growth, and transpiration is not necessarily translated in stem growth. And this was really interesting. Was for us was an eye-opener for how tree growth and how they use water and carbon. Okay, this is another study that we use, that we do with nitrogen in my lab, in my department, in my group. We specialized in nitrogen more than carbon and water. Nitrogen is our center of study. So we used 4 species that are 3 are native from Japan: cedar, Cryptomeria japonica, large, and beech, which is Laris campeferia and Fagus crenata. And we used 1 more species, which is black locust. This species is, as you know, a leguminous. So all these 3 species uptake nitrogen from the soil, but these 3 uptakes nitrogen from the atmosphere. So it's I think I remember the name in Japanese, but in English I don't remember how it's nitrogen fixate, nitrogen fixer, or nitrogen fixation. They do nitrogen fixation from the air, and these trees do it from the soil. So we have a combination of different species: evergreen, deciduous, coniferous, broadleaf, and we wanted to see all how these trees, what is their strategy when they use nitrogen. as you know, I'm not sure if you're familiar with this process. The nitrogen is absorbed from the trees, from the soil, to the trees, to the leaves. The plant uses the nitrogen for many functions during the growing season. But the nitrogen that is stored in the leaf after it's absorbed from the soil is not lost as litter every year, but I will say most of the nitrogen that is in the leaves is returned to the tree. So it stores in the stem, it stores in the root for the next year. So as you can see here, black locust, of course, takes nitrogen for free from the atmosphere, and they have the highest content of nitrogen in the leaves. They return very small nitrogen to the plant because they don't need to store nitrogen. But beech trees, for example, 72% of the nitrogen in the leaf is returned to the tree. Larch returns 50% of the nitrogen in the leaves, and cedar returns only 40%. So all this, this is how they go for season. The values I told you is cumulative. Okay, so the beech is 70% in total, the larch is 50%, and cedar is 40%. So even trees that grow under the same environmental conditions, the same soil, have different strategy when they deal with nitrogen. This is the soil depth. Of course, this is very logical. Sorry, if I'm not wrong here. Sorry, this is for beech and this is for larch. Okay, sorry, I forgot to write that. This is a very normal pattern. You have more nitrogen at the top, and when you go down the soil, the nitrogen percentage decrease. And this is the same for both trees. The only difference is that nitrogen in beech forest is much higher than nitrogen in large trees. And the opposite takes place with nitrogen isotopes. You have the lighter isotope at the top because it's more active, and the nitrogen of isotope becomes heavier at the bottom because carbon 14 is not so much used. This is something that we found very interesting. I don't know if it has been reported before. We tried to look for in the literature, but we didn't find it actually. But I'm completely sure this is not. We didn't split the atom here. This must be a process that must have been explained before. You know, this GL means green leaf period. This is pre-abscission, and this is post-abscission. So green leaf period means end of July, beginning of August. Pre-abscission means mid-October, and post-abscission means mid-November. So again, I didn't put it, but this is if I know beech. This is beech trees. So you have that from August to October, there is a decrease in nitrogen in the leaf, and it means that this part of the nitrogen has gone somewhere. So the decrease in nitrogen means because the leaf is still attached to the tree, so it means that this decrease in nitrogen has gone inside the tree. And it's very interesting to see that the root increases the nitrogen percentage. So the nitrogen that has disappeared from the leaves has gone directly to the bottom of the tree to store in the roots. And the next step, when the nitrogen decreases from October to November, that percentage of nitrogen that decreases is stored in the stem. So it's like you're filling a glass of water. The first water goes to the bottom of the glass, and the next will go to the upper part of the glass. So it's the same way. So it seems that it's gravity, that the nitrogen goes stored in the bottom of the tree, and the upper part goes filling up the tree. And this is really interesting. We observed it first for beech, but then we decided to do the same for larch, for cedar, for Robinia pseudoacacia, for black locust, and we found the same pattern for every tree. So this is a study done by a student, a master student, and also Felix did contributed to this study. So we wrote 3 papers actually on this topic using 4 species. So we try to find out with isotopes if we can follow the nitrogen. It's like a tracer. And we found that actually we can trace in the leaves. The beech species is a very nice tree to work with nitrogen isotope. Also in a stem, we could see several changes. So it's a very good tracer of nitrogen changing. But in the roots, we didn't find any difference. I don't want to go so specific with this. So I want you to that the first part of the graph remains in your head, that how the nitrogen distributes in the inside the tree after the growing season is over. So how they store nitrogen, and I am sure also they store phosphorus, of course, in the same way. And at the moment we are trying to do some studies with phosphorus to follow up the same way we did with nitrogen. Sorry, this is the graph I wanted to show you before. Sorry, I put it in the wrong part. Sorry to make this a bit confusing. Please go back in your minds to the study I did about the tsunami. Okay, so sorry for this. The blue part is the tree growth, and this, I'm not very good with colors. I think this is green. Is a carbon isotope. The carbon isotope. Okay, so it's very good match in tree growth and tree carbon isotope in the stem. So what is interesting here, we finished our study in 2014, and what is interesting here is that the carbon isotope doesn't seem to recover. Oh, sorry, the tree growth doesn't seem to recover, but the carbon isotope is indicating that the tree is recovering. The photosynthetic rate is increasing, so more carbon is absorbed in the tree. And according to studies on salinity or disturbances on forest, once the tree has been disturbed, all the carbon assimilation in the tree will be used or is used for recovering the parts that have been more affected. In this case, roots and leaves. So it's not that the plant is not growing. So it's a mistake to see the tree ring only as an indication of growth, especially under disturbances, because the carbon can be used also, of course, for growing more roots or for growing more leaves. And then when those parts that have been damaged are ready or are in normal conditions, that's when the stem is going to grow again. This was our prediction, that after some years, the carbon isotope was going to decrease and the tree growth was going to increase. But to be honest, our predictions were wrong, because the tree grew up to here. So the tree grew tremendously well, and the reason was that some of the trees in this forest died, so there was less competition for the trees that survived. For that reason, they could grow much better than before. I published this paper in 2018, so if you're interested, you can have a look at it in Isotopes in Environment journal. Okay, sorry, I close with that part. Okay, and this is a study. I don't know if you can see the letters very well. Sorry that I chose my choice of color was very poor. This is we did an analysis of 3 rings and isotopes in cedar and large forest in Shonai area for the last 50 years. So this is the cedar tree, very popular in Japan. You can find it almost everywhere. And this is the cedar is here at 250 meters, and the larch is usually in upper areas at about 650 meters above sea level. And if you can see it well, this is our building where we have our summer school, winter schools, educational activities. We have here carbon isotopes of trees of these 2 species, and here we found something really interesting. You know, these trees, as I told you before, they are growing almost in the same environment. Again, I mentioned before that carbon-13 is an indicator of you can use it as an indicator of stomata closing, and higher values indicate stomata closing, lower values indicate stomata more open, let's say. But this is a good explanation when you're using the same species for a certain time. But when you compare 2 species, that argument changes. It means here in this case that large trees are probably more they use more carbon, or they are let's say they are less water efficient than Cryptomeria japonica. So Cryptomeria japonica, or Japanese cedar, they do not release water for free like like larch. So larch is constantly uptaking water and releasing lots of water for that carbon. While Japanese cedar is a tree that let's say is more conservative, uptakes carbon with let's say less amount of water. So that's how you can see these 2 species. So let's say in the case that snow melt water decreases in this area, we assume that Cryptomeria japonica will be a tree that will adapt much better than large trees, because large trees are used to, let's say, waste more water for the carbon that they need, and the opposite is with cedar. And one more thing that we found interesting was that Japanese cedar for 50 years did not show any change in the pattern of carbon absorption, but we found an increase in larch from the year 2000. This is quite surprising because both trees are subjected to the same environment, but we found that for larch, there has been a switch, or there has been a change. And I forgot to show you some temperatures for the last 100 years in Japan. And in the 90s, there is a shift in temperature in Japan. So the temperature is not increasing in this way linearly, but is more going like a quick shift and then increase. And that's something that we have observed for not only this region, but for all Tohoku, or all northeastern Japan. At the beginning, we thought it was only for this region, but then we started checking temperatures for all northeastern Japan, and we actually realized that there has been a shift in temperatures at least in the 90s. For what reason, I cannot explain that. But this is actually a paper that I am writing with one Italian student from the University of Lleida. And we are trying to find out what is really happening here. And the same is for oxygen. Oxygen for these two species, usually heavier, like in the case of Japanese cedar, you have a heavier isotope, oxygen isotope, than for larch. So oxygen is a bit difficult for interpretation, because there are many factors that can alter the value of oxygen isotope in the stem. But it's interesting here to see that for the last 50 years there has been no shift in both species, and the most interesting is that both move at the same pace. So what indicates that both of them are completely dominated by precipitation water. So the precipitation water is exactly the same in both of them, but the way the oxygen isotope changes within the tree is different. So the way they transpire changes the value. The way they uptake water from the roots. So there are many factors that alter the value of the isotope within the tree. But as I told you, the tendencies in them is exactly the same. So this is a proof that both of them are strongly dominated by the high precipitation in this area. And the fact that there is no change in their pattern in the last 50 years means that at the moment they are well adapted to the changes in precipitation, and they are not under any type of stress. So you don't see any tendency here. We also measure nitrogen, which was also a bit of a surprise for me, because I have seen nitrogen. I have studied nitrogen for many years, but when I saw this, it was quite strange that until the 1990s, the nitrogen isotope more or less behaved the same for both three species. But from then on, the nitrogen in larch started becoming heavier, increased. I cannot explain this sudden drop. So I will focus more on this longer trend. But the same for Cryptomeria japonica, also the nitrogen isotope decreased for the last 30 years. Or decrease, I would say decrease. So there is a divergence of values in the 1990s, which we are not completely sure if it is because of climate, or it's because they both, after a certain age, are accessing different pools of nitrogen in the soil, or their mycorrhiza, after a certain growth of the tree, is fractionating, is changing the value of the nitrogen when it goes from the soil to the root, because this path is mediated by mycorrhiza. And it's something quite interesting here, because the Cryptomeria japonica uses arbuscular mycorrhizal, while large used ectomycorrhizal. And both of them have completely different ways to use the nitrogen that they are passing to the plant. So this is also a study that we are at the moment trying to put in a paper and send it. But for this particular nitrogen, I would like to collect more data because these values in this year are difficult to explain. So I would like to remeasure this part and see what is really the explanation, or see if it was measurements or it's the same value. Because it will be interesting to see why these values have such a sudden decrease, which is not usually observed for nitrogen. Sorry, this is again, this is the percentage of nitrogen. Here I have it would have been better to put this together, but I want you to keep this in your mind, okay? The Cryptomeria japonica goes down and the large goes up, which is exactly the opposite with the nitrogen content in the leaf, in the trees. So one of the explanations, now that I remember looking at the nitrogen content, is that until the 1990s, both trees absorbed the same, almost, let's say, the same amount of nitrogen, more or less closer. But from the 1990s, the Japanese cedar demands more nitrogen, while larch is not nitrogen hungry. Larch, I think, is one of the trees that survives with less nitrogen than all the trees that we have observed in this forest. Cedar beech is also highly demanding tree for nitrogen. So when in terms of nitrogen, I would say that larch is much stronger than other species because they can survive in very poor soils. And that's maybe one of the reasons why the whole taiga, Mongolia, northeastern China, are also dominated by large trees. I'm not sure if this is my last slide. No, this is another study of one PhD in my laboratory. We wanted to know between these three species, cedar, larch, and beech, what kind of water the trees are using. So this symbol here represents the oxygen isotope value of the rain. And this, in this, is the soil in each forest, as you can see here, soil in each forest. And xylem means that we extracted the water from inside the tree in June, July, and August, especially of the branches. The branches, the small branches, we cut the xylem and extract the water from the xylem and analyze the oxygen isotope. So we know which water is coming to the leaves. So, and it was very interesting that in June, the tree is not using precipitation water at all. So the tree is using the water that is coming probably from a snow melt or is coming from the precipitation that was the soil water that was already stored in the soil from the previous year. While in July, the tree is using soil water, precipitation, because the value of soil and plants and xylem is exactly the same as the precipitation oxygen isotope. So the shift on how the trees use water is quite different from month to month. And in August, we can say that the cedar and larch are using more water from soil and precipitation, but beech is using more water from the soil. because the values are lower in comparison to precipitation. This is a very interesting study. This student did a very difficult work because going to collect the samples was really terrible, but the conclusions were very clear. So this is a very nice study. I don't know if this is my last slide. I didn't want to leave you with a conclusion, so you can make up your conclusions in your mind. I hope you like the presentation.
Thank you, Larry. Thank you very much for the interesting presentation. And okay, there is a first question from Gabriel. Thank you for the presentation. Is there in Japan any evidence of forest pest and diseases shift that could be related to climate change?
Pest diseases. Pest,
yeah,
you
pest
mean, right?
and diseases shift due to climate change.
Yes. Thank you very much for the question. You know, tomorrow I am going to go to Zao Mountain. It's spelled ZAO. It's a mountain in Yamagata that has been, especially in the upper part, has been completely destroyed by bark beetle. It's a mountain covered by fir trees. It's called Abies sahalensis. Could be. This is something that we are looking at. That could be that the temperature has increased the occurrences of pests in this area. But we are. I am a bit skeptical about this idea because the tree age of this forest is 80 years old. 70, 80 years old. So it could mean that 70 or 80 years ago, there was the same pest that destroyed the forest and it regenerated again. So, and this is exactly what we are observing now, that the forest is regenerating. And we are using actually drone technology and artificial intelligence to count the number of trees or seedlings that are appearing in an area of about 20, 30 hectares of fir trees that have been completely destroyed. So this is a very interesting topic, and two of my students are actually doing this research. If you're interested about this topic, Gabriel, you can visit us in Yamagata, and we can go together to the mountain. It's a very, very beautiful mountain.
Okay, Gabriel is interested. Thank you for the invitation.
Yeah.
And there's a comment from Gent that thank you, Professor. Japan is an outstanding country indeed to learn about.
Yeah. For sure.
Okay, are there any questions? Are there other people thanking you?
Yeah, my thanks to you.
Oh, could be the isotopes used to analyze the seasonal change use of nitrogen or oxygen by the trees?
Yes, it depends. For example, if you use leaves, especially of deciduous trees, yes, it's quite possible to use nitrogen and oxygen isotope. For carbon, I will suggest that you use STEM isotopes. We have used 3 rings. I mean, not 3 rings every year, but we have cut 1 tree ring in several parts and analyzed carbon and oxygen isotope. For nitrogen, it's quite difficult to do that because the amount of nitrogen in the stem is very small. It's 0.1%. So we prefer to mix the whole ring and obtain one representative value per year. But yes, the answer is yes. We have done several kinds of those studies. I can send later my homepage, and in the homepage I have the publications that I have using isotopes.
Okay, that would be a great idea if you would like to share your web pages.
Yeah.
Perfect. Okay, are there any questions? Please don't be shy. It's your last chance to have your lecturer at hand. No questions, no comments.
Okay. If there is no question, I would like to ask one question. What is the, sorry, I didn't ask before. What is the background of the students?
We have different backgrounds.
Different backgrounds. Okay.
Yeah, it's okay. There is one question, one answer. Sorry, an electronic engineer from Gent.
Oh, sorry. We are doing sorry, what is the name of the electronic engineer?
Gent, I guess.
And hi Larry, it's Rosa Laura again. In general, they all have, or most of them have a scientific background, forestry, agriculture, geography. Most of them have a master degree, and I would say about 30% have a PhD, and only few have only a BSc.
Okay.
So usually the level is pretty high, and they are all more or less related to sustainable mountain development. So they are selected because they are dealing with mountains in different capacities, either because they're working in ministries or in national services or in NGOs or for UN organizations, but somehow they're all related to mountain development.
Okay. I was a bit doubtful to introduce some new research that we are doing now in my department. We are using drones and artificial intelligence together with a professor here that is a mathematician. And we are trying to develop a new methodology to evaluate forest, to calculate forest biomass, to evaluate forest health, including pests, which is what I was mentioning, to calculate thinning rates. So to basically automatize the system for evaluating forests, because Japan also is a very mountainous country, with 68% of the country is actually forests. So the rest of people and agriculture lives in the 32% of the country, and it's very difficult to access mountains. So we are actually in the process now of recruiting students from engineering background, because most of our students in natural sciences are not good programming or not very much in computer science. But we have now, of course, most of our students are in natural sciences, forestry, soil science, meteorologies, but we need the background of computer science. So if we have this group of students that come from both fields, then we can make a wonderful project. And this is now, if anyone is interested and have a good knowledge of Python or ArcGIS or any programming skill, we will be very, very glad to welcome you here for a short period of time or a long period of time, or to get a degree here with us.
Okay, Larry, it's very interesting. As Mountain Partnership Secretariat, we can for sure facilitate this. not only among the current IPROMO students, but also looking at those in the previous courses. So if you can send me just a short, and I'm sure also through the University of Torino with their links with the Polytechnic, I'm sure it shouldn't be too difficult. So if you can just send me a short email with the details of the features you're looking for, I would be very happy to share it.
Okay, wonderful, wonderful. Then I will do that this weekend.
Great. And I'm sure Michele and Danilo, I'm sure they also have other resources, but we can for sure share it within our networks.
Okay, okay, that will be really nice. I think it will contribute highly to mountain research.
Okay, there is another question. Another question: can you use isotopes to measure ecosystem age, not just individuals? Also, can you use isotopes to measure ecosystem work? From Antonio.
To measure ecosystem functions, you mean?
I guess.
Ecosystem. You know, basically, isotopes are tracers. So you trace the nitrogen that has been, for example, just to tell you about nitrogen, the nitrogen that has been at certain depth in a soil layer, and you trace it where this nitrogen ended up. It ended up, stayed in the stem, stayed in the leaves, it's in the litter, went back to the tree. The same is with water. If you have snow, you have rain, you have underground water. If you have water that has been stored for some time in the soil and you want to know which water the tree or the plant or vegetation are using, then you use oxygen isotope to trace that water. So as a tracer, you can use it for to investigate many functions in the ecosystem. So the uses are multiple, and it depends on the objective of the study. But for isotopes can be used for many to investigate many functions in an ecosystem.
Also, there is the specification from Antonio. We would like to clarify: understanding work as energy consumption by time unit for a specific function.
You know, this is a very interesting question. The isotope is not usually a measure of quantity. It's more a measure of quality. So it's very difficult to quantify. For example, in this slide that I am showing you, I can say that the tree is using water from the soil and not water from precipitation, but I don't know how much water they are using. So it's very difficult it's a help to understand the origin or the origin of the element that you are studying, but it's not designed to quantify that element. So for energy, I would say you can complement it with another measure, and then it could be very useful.
Thank you. Thank you.
Okay. Thank you very much, Larry.
Yes.
And thank you very much to all the participants. This is the last lecture of this first strange online IPROMO course. And okay, it's very strange because we had 12 edition on site, working on mountains and having people in the class. So it's, for us, it's really strange to have this kind of lecture, but we are trying to adapt and continue this IPROMO adventure. And if Rosa Laura and Michele would like to add something before closing this session, I would like only to close by inviting everybody for tomorrow in the closing ceremony at 2:30 p.m. Rome time zone. So please, Rosa Laura and Michele, you are welcome here if you want to add something.
Well, I just thank again Larry. I hope you can join us for the closing ceremony. And I also hope you will be able to join us in the Italian Alps for a face-to-face course in the coming years. That's been a real pleasure, and I hope we can stay in contact. It has been a very interesting lesson, and thank you very much from my side.
Thank you very much.
Thanks also from my side, Larry. It was really nice and interesting, your lecture. I'm really looking forward to see you in the mountain next year. Hopefully.
Yes. As soon as the permission for us to visit Europe is lifted, you know that I love Torino, so I will go to Torino right away.
You are welcome, of course. Okay.
Thank you.
Okay, thank you again. Now I'm opening the microphones so everybody can clap their hands and say thank you.
Thank you.
Interesting. See you tomorrow.